Hello everyone, I'm Jiaqi Gao, a fourth-year PhD student at Harvard University. Today I'm going to present Lyra, a cross-platform language and compiler for data plane programming on heterogeneous ASICs. This work is done during my internship at Alibaba. Recently, programmable network devices have gained significant traction in the networking community because of their high performance and high flexibility. People have shown the tremendous benefits brought by the flexibility of programmable network devices, for example, consensus protocols, load balancing, network monitoring, storage, and congestion controls. All of the mainstream vendors are releasing their own programmable ASICs. However, despite the bloom of the programmable network devices and languages, we found that the foundation of network programming on data plane is still at an early stage. Just like the era when the programmers coding the software on CPU using the assembly language, network programmers are still using chip-specific languages and manually take care of the numerous details with hardware features, capacities, and network environments. In general, there are three problems when programming the data plane. The first problem is portability. Current data plane programs are tightly coupled with specific ASIC models from specific vendors. It cannot migrate across different programming languages, such as Trojan 4 supports NPL, while Silicon 1 supports P4. It also cannot migrate across different chip architectures with same language support, such as Silicon 1 and Tofino, and sometimes cannot migrate between different models by the same vendor, such as Tofino and Tofino 2. As a result, programmers are required to be proficient in all the data plane languages and all variable architectures and resource constraints of different ASICs. The second problem is the extensibility, which means to distribute a program across multiple switches. Low-level languages focus on programming individual ASICs, while there are data plane programs that require to execute on multiple ASICs in a distributed way. For example, a network service chain may assign different roles to different switches, such as firewall, gateway, and load balancer on each of the switches. On the other hand, applications such as firewall can also collectively use table resources in multiple switches for accommodating large-scale workloads. Nowadays, programmers have to individually program each switch data plane. Last but not the least, the practical deployment of the programmable data plane must have multiple programs enabled. For example, the programmer may wish to deploy both the ARP function and firewall function in the same switch. Currently, the programmer has to manually merge the programs together. We believe the fundamental reason for the above three problems is the lack of a high-level data plane programming language. Like we've said before, the low-level chip-specific language is the same as the assembly language that is specific to the architecture. Just like Dr. Brand said, the C language lets you get close to the machine without getting tied up in the machine. So now it's time to propose the high-level data plane language. So here we present Lyra, a high-level data plane programming language and compiler. Lyra offers a one-big pipeline abstraction. It is the interface we provide to the programmer that hides the pre-mentioned three challenges. The programmers only need to write down their intent through the Lyra language. The Lyra compiler can solve the three challenges and compile the program into the chip-specific program for each switch. Let's first see why we need a new abstraction. Traditionally, there are two models of the network. The first model is a per-switch model, where the programmers program each switch individually. And as we introduced before, this model is too fine-grained and brings many challenges. On the other side, we have the one big switch model, which treats the whole network as a giant switch, and the switch is only in charge of delivering the packets between the servers. This, on the other side, is too coarse-grained that we cannot control where to allocate the programs, such as deploying an ARP table to all of the TORs. So we choose a one big pipeline model that provides a good balance that gives enough flexibility to the programmers, but not let them tied up to the detail of the topology. The one big pipeline model achieves the portability because it hides the switch chip information. In this model, programmers no longer need to worry about how to split the code between switches. Here, the programmer can simply assign the firewall to be deployed in these two switches and deploy the pipeline of code in the red scope. At last, the programmers can simply composite multiple programs together by overlapping the deploy scope of the pipeline. In this case, the programmer can deploy the ARP program in each Tor switch. Now let's see how the Lyra compiler compiles the program into the chip-specific low-level languages. The Lyra compiler has two components, the front-end and the back-end, and here is the input Lyra program. The front-end translates the input Lyra program into the intermediate representation. The Lyra backend compiles the intermediate representation into a data plane program on each switch. Let's take a closer look at the backend of the compiler. Remember previously, there are three challenges: portability, composition, and extensibility. The backend introduces three components to solve each challenge. Lyra first builds one language synthesizer for each language, such as P4 or NPL, to synthesize structured chip-specific programs. Because the low-level languages have different programming paradigms, we need to develop the language synthesizer in parallel. For example, to synthesize a P4 program, we introduce a special data structure called the predicate block. Next, Lyra uses a chip-specific constraint encoder to check whether the program can fit into the switch. To achieve this, we implement one encoding algorithm for each type of resource to estimate its usage, such as the packet header vector, SRAM, TCAM, etc. Please refer to our paper for the complete list. At last, the distributor uses the topology and the pipeline deploy information to deploy the program across multiple switches. The backend uses several constraints to make sure the program is correctly deployed in the network. For example, the upstream switches have to pack downstream required information in the packet header so that downstream switches can process the packet correctly. The above three components encode the input Lyra program into an SMT formula, and the SMT solver returns a valid allocation plan. At last, this allocation plan is translated into the data plane program running on each switch. To evaluate the performance of the Lyra compiler, we wrote Lyra programs for applications such as netcache, netchain, and even switch.p4. There are two takeaways. The first is Lyra program requires way less line of code than P4 program. We can see from this table, Lyra saves 30% to 80% line of code compared with the P4.14 implementation. This is because Lyra uses a more compact language framework and a one big pipeline model. The second takeaway is that Lyra can reduce resource usage. We can see that in the netcache example, Lyra uses only 12 tables, while the original program uses 96 tables. We observe similar gains for other programs such as netchain and speedlight. This is mostly because the manually written version kept many independent tables for modularity, but Lyra merges these independent tables together into a single table. Here is a code for netcache. We can see that there are two tables with no matching field. And because they are executed under different branches, they can never be executed at the same time. The Lyra can merge these two tables into one table and two rules that matches the nc_hdr.op field, which is shown on the right. We also evaluated the scalability of the compiler. Please check our paper for the result. Here summarizes the can and cannots of Lyra. Lyra can generate the data plane program for the entire network. It supports P4.14, 16, and NPL data plane languages. And it supports both stateful and stateless operations. It can also reduce the resource usage compared with human-written programs. But Lyra is not responsible for generating the control plane programs or configurations. At last, currently Lyra generates data plane programs from the beginning and does not synthesize incremental changes. In conclusion, Lyra is the first high-level data plane language and compiler that achieves portability, extensibility, and composition. Lyra offers a one big pipeline programming model and can generate runnable chip-specific code across multiple switches. The programs generated by Lyra use fewer hardware resources than human-written programs. Thanks for listening, and I'm happy to take questions.
Thanks a lot for the talk, Jiaqi. So to start our discussion, I want to hear your thoughts on the comparison before Lyra and Macro P4, because both papers are talking about portability, composition, and modularity. So from a high level, people can see a lot of, a lot of things in common between these two works. So I want to hear what's your opinion and what do you think and what do you think of these two languages?
Yeah. So I think just like previously, he said that micro P4 focuses on composition and portability because it can port between different P4 architectures. But Lyra, I think it's sitting at a higher level since it can achieve not only portability and composition. The most important character is it supports extensibility, which means you can deploy the program across multiple switches. And I think this is one major difference. The second is I think micro P4 uses a modular approach, just like you said. And the Lyra actually chooses on the other extreme, which is a procedure-oriented programming paradigm. So I think this is majorly a difference between our design choices because we are actually targeting on solving different problems rather than solving the problem in different angles rather than trying to use a similar approach to solve the same problem. So I think, yeah, basically that's the difference between the Lyra and the micro P4. Yeah.
Okay, so the next question is from the Zoom QA window. The first one is from Juan, and the question is, would you say the Lyra program is a control plane program and the Lyra compiler is the interface between control and data planes?
I think still no, because when the programmers are writing the Lyra program, actually what in their mind is the data plane functions rather than the control plane. So I always have this example of using for example, Quagga, right? So Quagga is a BGP control plane program, and actually Lyra is not responsible for writing those type of programs. The programmers have to write what the data plane, actually the BGP tables. They have to describe what are the tables and how the table behaves in the data plane rather than thinking about the control plane or the control plane and data plane interfaces. However, Lyra do provide the interface between control plane and data plane, but rather than this is a way for the programmer to control the data plane objects rather than it's like the control plane and the interface between control plane and data plane. Yeah.
Great. Okay, so the next question is from Niranja. And the question is that in the paper, you compare mapping efficiency to different languages. So the question is, what features of the hardware or language result in the efficiency improvement?
I see. So it's what is the feature? So the feature, actually the component that reduces hardware resources is our synthesizer. Because as we said in the evaluation, so take the net cache example. So there are always, I think because of the modularity concern, like people are trying to, because previously P4 is the only interface that both for the compiler and for the programmer. So it has to be both readable and understandable for the data plane. So people tend to read more modularized code. For example, they have a section called like routing. They have a section called access control, something like that. But in reality, you can sort of merge those multiple tables together into one single table. And this is where the compiler is helpful. The compiler can explore such, how should I put it, parallelism and then merge it into one table without affecting the whole program's functionality, and this can reduce a lot of hardware resources.
Yeah, great. Okay, so there is also someone asking whether Lyra is an open source language and compiler that is available on GitHub that people can play with and do research. Yeah.
So unfortunately, currently Lyra is not open source, but we are, because it is a company, how should I put it, because Alibaba is using it internally, but we are working on it, try to open source it and make it more concrete, more functional. Like I think currently it's a prototype and it works for, it's not so generalized, and we are trying to perfect it in the company, and we will publish it eventually. Yeah.
Great. Okay, so we will have the last question. The last question is Mina, and the question is can Lyra, how does Lyra make sure that the partition programs fit into the switch? Because for targets like Tofino, there are some constraints that which are not very easy to express. And because of that, you want to know if a program will definitely fit without compiling it in the first place.
Yeah, so I think this is what we are trying to do. Actually, we are trying to propose a set of constraints that after you meeting this constraint, then you can fit it into the switch. So actually, according to our current experience, like we encoded many constraints in the Tofino, and we put the RMT version because of open source architecture into the paper. And I think SMT, on the one hand, SMT solver is powerful enough to encode all of the constraints we currently know. And secondly, from our current experience, all of the programs that as long as it go past SMT solver says yes, then the compiler will say yes. The compiler will say yes to our program. So I think currently this problem does not exist that severe. Like we don't find a program that SMT solver says yes, but compiler says no. And actually, from our findings, the SMT solver can guide the compiler to fit the program into the switch, into the switch, right? So sometimes the compiler cannot find it is because the compiler may misconsider some resource allocation strategy, but SMT solver, because it takes longer time or it is easier for SMT solver to solve it, then SMT solver can somewhat find this kind of allocation strategy, and then we can guide the compiler to fit it into the switch.
Yeah, thank you. Thank you very much, Jiaqi.
All right, thank you, Jiaqi. So we've got a couple questions on Slack that we can get into. So one of them is, what's the key advantage of the one big pipeline abstraction? So does it need to sacrifice something else in order to get its gain?
Okay, so great question. So the key advantage of one big pipeline abstraction is way more flexible than the two other approaches, which is the per switch view and the one big switch view. So the thing sacrifice, I think we there's nothing to sacrifice actually in this case. It's just it takes a little bit more effort to build a compiler rather than the previously engineers had to either code program on each switch, or they have to completely sacrifice the whole programmability because they hold a global view of the switch and then merge it into one big switch.
Got it. Thanks. So another question that was on Slack. So on slide 9, you had two examples, or you had a firewall and an ARP. Yeah. Are those considered two Lyra programs, or are they independent functions to be composed?
Yeah. So right. So these two, we are calling it. I think we are calling it two pipelines because they are independent, and they are. First of all, they are independent, and the Lyra compiler just compose them together and compile into one program for each switch. And I saw that in the question that it's possible to create a library of Lyra. So I think this is definitely one thing possible, and this is definitely something that we are already done actually. So we do create a lot of a set of predefined library for the commonly used functions. For example, ARP protocols, for example, firewalls, etc. Yeah.
Great. So there was one question that I was really curious about. So so my impression is that translation from P4 into data plane configurations potentially involves a lot of complexity within the compiler. So how do programmers or your system handle those potentially complex constraints that are potentially black box inside the compiler?
Yeah, so I think we as the compiler developer, we need to know the exact detail about how the for example, Tofino compiler, how the Tofino compiler compiles the P4 program into the binary that can be burnt into the chip specifically. For example, we have a detailed list of how to compile the RMT open source architecture, like what are the constraints available. And the method we use is to encode it into SMT formula. And the SMT model, the first order logic is quite powerful, and they are quite expressive. And currently we don't see any constraints that it's not encoded by the SMT solver. So I think, yeah, to answer your question short, we need to know the compiler programmer, they need to know the detail of the chip, and the compiler is using SMT solver to encode such constraints.
Got it. Great. That's super interesting.